Okay. So in the previous class, I think we discussed about the comparison of LED and other laser diode. So which are all nothing but the sources. Okay. So sources is that to carry information. Huh? Okay. Next, our topic is photo detectors. So what are these photo detectors? Basically, what is a photo detector? So you all have seen it and seen it in sense. You all know what is a photo detector and how, what are the different types, and you have studied all those things. Anyhow, we'll study. So as you know, so photo detectors, the name itself tells you photo. It's a light detector. So detection of your light. So whenever detection of light means it always comes at the receiving end. The source till now, whatever we studied was optical sources. Optical sources that comes at the transmitting side, whereas this photo detectors comes at the detector side. So at the receiving side, there should be some sort of mechanism or a device which is going to detect the signal, and it is going to interpret whatever the information that is contained in the optical signal. So such a device, we call it as an optical device. Okay. So here basically what it does. So basically, therefore, I think stage. Okay. Uh, so the here the devices going to sense the luminescent power. So that's what I was telling you. So here photo detectors, these are the devices which is going to sense the luminescent power. So luminescent power is nothing but light power. Okay, light that falls upon it. So based upon the light that is incident on the device, it will convert the variation. What kind of variation? Variation of your light. Variation of your light. So it converts the variation into its corresponding varying current. Varying current with which we can get the original information, which has been transmitted before the source. Fine. So let us see some examples. So what are the examples? So there are many photo detectors. Okay, but all the photo detectors cannot be used in all purposes. Why? I tell you a little later. Anyhow, so the examples for your photo detectors are photomultipliers, pyroelectric detectors, photoconductors, phototransistors, and photodiodes. So the last three you know already. These things you have studied in your third semester itself. The photoconductors, phototransistors, photodiodes. These are all semiconductor based. Semiconductor based. Fine. Yeah. Now, as you know, these optical detectors, whenever it is being used, it should have that means some properties it should possess so that it can be used accurately. So what are the basic requirements? Okay, since whatever the signal that it comes from your fiber, it is very weak in nature. Weak in nature means what? Since it's being traveled a long distance, and there will be some attenuation and all those things. So whatever the photo detectors that we sorry, use. So since the signal is very weak, these photo detectors which we use, it has to take that signal and it has to convert. So what we have to do, the signal that is the photo detector, you should be sorry, able to catch the smaller signals, and it has to convert the smaller variations also. It has to consider the smallest variations and it has to convert into its equivalent electric signal. Okay, so basically it should have a high fidelity. And next, high sensitivity. High sensitivity at the operating wavelength. So what is this high sensitivity at the operating wavelength? That means whatever signal that we get, it should have a higher sensitivity within the range of the optical source being used. See, there we have so many wavelengths or so many with this, it might come, but it has to sense or it should possess a sensitivity or a higher response in the a particular operating wavelength. Sorry, we have mentioned operating wavelength. So either it may be 810, 1310, 35 or something. That like that, it has to work in a particular window. That is what it means. That means it has to show a high response or sensitivity in the range of the optical source. You know what is the source wavelength that is being used. Okay. So next comes your high reliability. That is always it should because if at all if it changes into something else, if it's not changing it's into its equivalent signal, then I think you might see or you can feel the output, right? So if it says so for example, open the door. If it says it close, it's reverse. So something different. So that's why it should relay. Relay means it has to be accurate and all those things. Highly reliable, a small size. That all. A small size. That is our this thing. Okay. And low bias voltages. So bias voltages should be very less. The larger electrical response to the received optical signal. So the electrical response should be very large to the whatever the received signal, optical signal. See, even though the signal is very weak, but the received electrical signal should be very large. Okay, and minimum noise introduced to the detector. Okay, it should be what I can say is should be able to uh, uh, give a minimum addition of noise to the system. Fine. Then and low cost, as you all know. Then it should be compatible with the physical dimensions of the fiber. So this is very much important thing that we need to know. So you will be having a photo detector, but if at all it is not feasible with the fiber that the information coming from the fiber, that fiber. If it is this photo detector is not compatible with the fiber, then I think you can't extract the information from the fiber. So it is best that it should be seen that whatever the device that you have, it should be compatible with the dimensions of fiber. And also last, as a human being, we need any device for a smaller size, low cost, and long operating life. Like similarly, that also we need a longer operating life. Okay. As I was telling you, there are n number of devices, photo devices in existence, devices in existence. But all the things we are not going to make use. I was telling earlier only that all the photo detector in market you cannot make use. Hmm? They may be photo multipliers. You know what is a photo multiplier. For example, in CRO and all the things there, you will be using a photo multiplier so that the beam will be having a high intensity and it will show. For it will if you I think now the syllabus is changed for you. So you people have not studied these photo multipliers. Anyhow, there the multiplication factor it is going to reflect n number of times or n number of times, 1, 2 times, 3 times based upon the multiplication factor that you need, due to which the incident beams get reflected multiple times and they are kept in a particular angle so that you can achieve a more number of uh, what I can say, it multiplies many a times and you will be getting a higher output. So that is what a photo multiplier. If you want, you can Google and you can check out, or you can refer textbook in the courtesy textbook. There you have photo multipliers. Okay, pyroelectric detectors. Okay, and next the so what is particular pyroelectric detectors is, so these pyroelectrical detectors basically it converts the photons that into heat. So that is not our requirement, because we need to have for communication purpose, not to convert that into heat. Right? Whereas your pyroelectric detectors that uses, for example, here you have say taken pyroelectrics, photomultipliers or next is pyroelectric. So this pyroelectric, it is going to convert whatever the incident photons that into heat. So here there will be a change in the temperature. Change in the temperature, and that means whatever that result that comes from the temperature change, that will give a variation in a dielectric constant, which will be measured. Yeah. Okay. The response of the detector, it will be quite flat. So this photon, that is a pyroelectric detector, will not be using. Next is for semiconductor-based photo conductors, phototransistors, photodiodes. These are all there. So all these things are there, but still it cannot be used. Okay, so which is the one which you are going to use? The photodiode. Photodiodes, they are the one which is being exclusively used for our fiber optic. It is being exclusively used for our fiber optic. Why this photodiode are exclusively used instead of other that means photodetectors? It is just because of its smaller size and suitable material. That is what I was telling you. It should be compatible with the physical dimension and process. So that is what here, the suitable material. It has got a higher sensitivity in the operating range. So it can be tuned. The this material, it can be tuned to a particular wavelength. Okay, that means you can manufacture. That is what has to high sensitivity and suitable material and the fast response time. So the response time is compared fast compared to some others. Hence, these photodiodes are the one majorly used for detection of your light signals in a receiving end. Okay, the different types of photodiodes. So if you are studying photodiodes, then which are the different types of photodiodes and which one and what is the types and what is the difference between those things that will see later. That is the one is the spin photodetector and the other one is avalanche photodiode. So these things you are all have used in the laboratory I think, and also in your few mini projects. This spin photodetector, avalanche photodiode. So yeah, I think you have not done it first year lab, I feel, right? So there you would have used. So next comes your spin photodetector. So what is a spin photodetector? Okay, the basic principle, as you all know, photodetector. So as this diagram you can see the construction features. So the construction feature, by seeing this, what you can see, what you can tell me. So here, as you all know, here by seeing the diagram, you can see there is a P device and a N device. In between, there is a large gap. So, which is a very lightly doped N-type N-doped intrinsic region. That is the I region we call the PIN. So pin photodetector. So you will have a P region and the N region in between a intrinsic region in between. Okay. So this region is a very lightly N-type doped devices. So here you can see, yeah, suppose whenever the signal or a photons, if it falls on this, there will be a moving of these charge carriers, either the hole or the electron that moves to the either side, right? So the device basically it consists of P-type and N-type semiconductor region separated by a very lightly endowed intrinsic region. So intrinsic, that's what I region. So during normal operation, usually a reverse bias voltage will be applied across this device so that no free electrons or holes exist in the intrinsic region. So initially there will be no charge carriers, right? Either free electrons or holes will not be there. Since you have applied a reverse bias voltage, all the charge carriers will be moved. So, as in when your incident photon having energy greater than or equal to, if it is having a less energy than the band gap energy, then there will be, sorry, no movement. So, whenever it is equal to the band gap energy of the semiconductor, it gives up its energy and there it excites the electron from the valence band to the conduction band, and hence it results in a current. Okay. So excites energy from them. So this process it is going to generate the mobile, that is the movements of the charge carriers, that is the electron hole pairs. This is known as the photocarriers. These either electrons or the holes. These are all electrons and the holes. These will be called as the photocarriers, and these generated carriers are available to produce a current flow. That is what here current flow when a bias voltage is applied. So in the previous slide, I was telling you low bias voltage. So it should operate here for a smaller bias voltage. Okay, even though if you apply a smaller bias voltage, it has to move. The charge carrier has to move. So it produces a current flow. So when it is going to produce, whenever a smaller bias voltage, it is been applied across the device. So here the number of charge carriers that is being controlled by the concentration level of impurity elements. Elements. Okay, so here it can control the charge carriers. How you can say that you can control in the previous while telling you lasers also I was telling you that it can be controlled. So I think I had explained there also. I'll tell you once again. So here it can be controlled. How it can be controlled? It can be controlled only through the concentration level. So by varying the concentration of impurities. Okay, that is what. So this photodetector is normally designed, okay, so that these carriers which are being generated, they will be mainly in the depletion region. Okay, so the current flow will be there. Either the current is shown as the LN or LP or whatever. That is what. So next comes your this one. Here you can see the depletion region, the band gap, and the valence band. So whenever it moves greater than the band gap energy, it will move from conduction band to valence band to the conduction band. Right. So by seeing this, what is this? This graph, okay, that is the energy band diagram. What you can infer? What you can infer? What you can infer? Can anyone interpret? So here you can see the photon is incident, the generated hole. So whenever a incident photon, okay, which is having energy h mu greater than energy band gap. That is what I was saying here. So if it falls, it able to boost an electron to the conduction band. So it moves, or it is going to boost an electron to the conduction band. This is from the valence band to conduction band. Only whenever your energy is greater than the band gap energy. After a certain voltage, that is beyond a certain, the light cannot be absorbed by the material. So that is what it is operating in the particular wavelength. So it can, beyond a particular wavelength, the light will not be absorbed by the material, as the wavelength of the photon is inversely photon. You can see a wavelength. It is inversely proportional to the energy. So a particular semiconductor material, suppose if I use here one material, for example, in the next slide I will tell you, I will show you the different materials having different energy and band gap, okay, band gap energy. So that's the reason semiconductor only over a limited wavelength region. So that is the advantage also. Here you can see that we have mentioned uh, operating wavelength, high sensitivity of the operating wavelength. So it operates at a particular wavelength, whereas it is not going to absorb or move the electrons in a different wavelength. So that is what here you can see. Fine. Next, uh, this detector. Again, and tell you later. There is in the textbook there are some problems related to very small, okay, small expressions. So the photon absorption coefficient, that is okay. P of x, okay, the power level at a distance x into the material is Px is equal to, the expression was difficult, so I have not written. Anyhow, you can note down if you want. So the power level at a distance x into the material is P of x is equal to P into exponential minus alpha s into x. X is the distance. Okay. So alpha s is the photon absorption coefficient. So this alpha s, it again it depends only on the wavelength. This is known as photon absorption coefficient. And also lambda c is equal to hc by eg, that you know, so which you can calculate the lambda. Fine. The next, and also efficiency, that is the quantum efficiency. Quantum efficiency is given by number of electron hole pairs generated divided by number of incident photons. This already we have worked in the source. It is also similar here. So again, I will not solve the problem on those. So number of electron hole pairs generated by number of incident photons. That is what your efficiency. That is the quantum efficiency. Right. So next comes this detector response time, I tell you. So next comes your avalanche photodiode. Okay. What is this avalanche photodiode? Answer, yeah. So what are these avalanche photodiodes? I think you all have studied, right? What is this avalanche photodiode? So here in this avalanche photodiode, just like it is same. Yeah, I will tell you here. It is similar to your pin diode only. The difference between your pin diode and here you can see the diagram here, NP, I, P plus. Here some small variation, but it's somehow some basic principle is just like your pin diode only. Pin diode only. The exception is the addition of the addition of high intensity electric field region. Okay, high electric this region. So what this high intensity electric region does? So in this, basically in this region, here the whatever electron ore pairs that is being generated due to the incident of electron photons, they will be able to absorb the its energy, that is the kinetic energy from the a strong electric field in order to collide with the atoms present in the region, which generates more electron pairs. So here they make use of extra high intensity region in order to generate more electron uh, pairs. So that is carrier multiplication. How you might ask me how it is going to generate more electron volt pairs. So it is all due to the carrier multiplication. Multiplication happens. How it happens? It is due to the impact of the ionization that takes place within this ionization that takes place. Okay. So if at all we have applied a very high field, the depletion region. So here you can see the gain, it increases and finally, okay. So like the electric field versus distinguishes. So in the depletion region, a field, it can discharge more free electrons in the atom. So it gains a higher kinetic energy in order to ionize other atoms. So results in an carrier multiplication. So uh, carrier electron hole pairs are morely generated, due to which more number of electron hole pairs are generated and moves. So here you can see, here it is a substrate. P plus is the substrate. You can see I region. That is what you have seen in the previous pin diode. Here also it is a material with a lightly doped intrinsic type. Okay, and this is a P region here. Okay, it's a P region which we call it as a high resistance epitaxial layer. We call it as a high resistance epitaxial region, and the last is this is N region, that is a heavily doped layer, heavily doped region. Okay, so here you can see, yes, you can see the region, that is the electric field versus the distance. Here you can see it increases. So this P is the highest resistance region where we will be getting in this junction in between a avalanche region. That is more number of electron hole pairs are generated. So uh, this region we call it as an avalanche region. That is minimum field impact ionization takes place, whereas this is the depletion region. Whenever we apply a bias voltage, we will be getting a avalanche region in this, whereas the rest of the region, this from here to here, it will be a depletion. Fine. So whatever the applied voltage that we apply, it will be across this P and N plus region. So based on this, the voltage that we apply, this depletion region here, the depletion region, either it widens and it reaches the I region. Okay. As in when light enters this P plus region, it will be absorbed in I region. That is, it acts as a collector. This I region, since it's lightly doped, it acts as a collector region. Fine. So this is what your general information. The same thing I have put in words. So in this region, primary electron volt pairs are generated by the incident photons. It is going to absorb kinetic energy from strong electric fields in order to collide with the atoms present in the region. It generates more electron hole. So the physical phenomenon behind the internal current gain is known as the impact ionization. So impact ionization leads to avalanche breakdown in ordinary reverse bias. That is what it here told, and that is what. It requires very high reverse bias voltage in order to the new carriers are created by impact ionization. So what is this impact ionization? The phenomena behind the internal current gain. Okay, that is what. So due to which generates more electron hole pair from incident photon through ionization process that we call it as the avalanche effect. So this avalanche effect, it is going to create a multiplication of the results, and that is causes a amplification of your photodiode current. So next comes your multiplication factor. So what is this multiplication factor? So you might see this multiplication factor M, it is given by Im by Ip. So what is this Im by Ip? So this multiplication factor M, it is the measure of the internal gain provided by APD. APD is avalanche photodiode. So it is the internal gain multiplication factor. So basically it is defined as the ratio of total multiplied output current to the primary unmultiplied current. So that is Im by Ip. Okay. Right. Next is the ionization rate. So what is this ionization rate? Ionization rate, ion is nothing but the number of electron pores which are generated. So by a carrier per unit distance. If you take the number of electron hole pairs generated within a single unit distance traveled, that we call it as an ionization rate. Okay. So the number of the electron hole pairs that is generated or created within a particular unit distance traveled is called the ionization rate. So photodetector materials. Next here operating will. Okay. I can continue, right? Hello. Shall I continue for another 5 to 10 minutes?
Sir, we have classes from 2 o'clock, sir.
Two. Why two? It's from 2:30, right?
It is supposed to be 2:30, but I don't know, sir. Yeah, it is scheduled for 2 today.
Who?
A German class, sir.
Okay, fine, fine. So shall I stop here? I
Yes,
thought
sir.
of taking another 5 to 10 minutes and complete this chapter by today, and start the next unit by tomorrow. You know, 140. So another 20 minutes will be there. Okay, you carry on. Tomorrow I will continue this photo detector materials. Is that okay?
Okay,
Okay. I'll stop at this point here.